Okay, this is the second video on section 2.5. We're going to look at a couple examples of physical applications. So we're going to start off with Hooke's law. And Hooke's law states that the force required to compress or stretch a spring is proportional to the distance x that the spring is compressed or stretched from its original resting length. So you have force is equal to kx. K is going to be the spring constant, so that'll be dependent on what kind of spring we have, and then X is going to be the distance the spring is compressed or stretched. So we have, here's our string and it's at rest, so we can say that's an equilibrium. Or we have our spring compressed, okay, or compression. Or we have our spring stretched out. So we have a stretch. Okay, so let's try an example out. Okay, so it says a force of 3 pounds compresses a 12-inch spring 2 inches. Part A says how much work is done compressing the spring 7 inches. Okay. And then part B, we're going to figure out how much additional. So we compress it 7 inches. What if we compressed it all the way down to 10 inches? So from 7 to 10, how much additional work is required to compress that spring? All right, so we'll start off with force is equal to kx. So a force of 3 pounds compresses the spring 2 inches. Okay, so the 12-inch spring doesn't really matter for this part here. Okay, so we're going to have 3 over 2 when we solve for the spring constant. So 3 divided by 2, and that is going to be a force in pounds, and then divided by the 2 inches, and that's going to be our spring constant. So our force is equal to 3 over 2. X. So if we want to find the work is going to be the integral from A to B, force times the distance. So it's going to be the integral from 0 to 7 because we're compressing it from its natural position, 7 inches. 3 halves x dx. So when we integrate that, it's going to be 3 over 2 times x squared over 2 from 0 to 7. That is going to give us 147 over 4, which is about 36.75, and that is going to be in inch pounds. Okay, so inch pounds is going to be the units. Okay, for part B, the work, we're just going to go from 7 inches to 10 inches. So we've already compressed it to 7 inches. We're going to go to 10 inches compression. So 3 halves x dx. All right, and so 3 over 2 times x squared over 2 from 7 to 10. Okay, so 300 over 4 minus 147 over 4. So it's going to be 153 over 4, or that's approximately 38.25, and that's going to be in inch pounds. And that seems to make sense. The more you compress the spring, the more force you're going to have to apply, so we're going to have to work harder compressing that spring. So we used less work compressing the spring from its natural position down 7 units. We used more force to compress it from 7 inches to 10 inches than from its resting base to 7 inches. Okay, so that is an example of a spring problem. We're also going to look at lifting objects, and that'll be in the next example here. All right, so let's go ahead and speed it up a little bit. Okay, so it says how much work is done lifting a 40-pound object from the ground to the top of a 50-foot building. If the cable used to lift the object is 1.5 pounds per foot. So we'll go ahead and put our weight in. Weight is 40 pounds. And then there's our chain. And are we using a chain? What did they say? Oh, well, we're using a cable. Okay, so we're going to draw in our cable. And that 40-pound object is going to be lifted up. And the chain weighs 1.5 pounds per foot. Okay, and so again, it's going to be the force required and then times the distance. And so for our force, okay, we're going to be taking that 40 pounds. Okay, so we're going to be taking that 40 pounds. It's always going to be 40 pounds the whole time. And the cable should probably be a length of 50 to get it all the way up to the top of the what are we doing? Moving it up on the building? Yeah. Okay. So as it is, the whole weight of what we got going on is 40 pounds for the weight, and then 50 feet of cable, which weighs 1.5 pounds per foot. So that total weight here, we can think of that as our force. So a weight is a force. So it's the 40 pounds for the weight, and then 50 times 1.5, and that's going to be the cable width, force. Now, as we're rolling this up, as we're moving that weight up, okay, we are winding up some of the chains, so some of that weight is lost as we're going up, so we don't have to account for it anymore. So what is happening is each foot we go up, we are losing 1.5 times x, where x is in feet. So each foot you round up, you wind up, you're losing 1.5 of the total weight there, because you're not having to move that piece of cable anymore. Okay, so that's our force. And so our force equation is going to be 115 minus 1.5x, and that's after I combine my like terms. I did 40 plus 50 times 1.5, that's 115, and then minus the 1.5x. So the work done, we're going to move the object from 0 to 50 feet, okay, and there's your force, there's your distance, and all we got to do is integrate this. It's going to be 115x minus 1.5x squared over 2, evaluated from 0 to 50. So 115 times 50 minus 1.5 times 50 squared, all over 2, minus, and we plug in the lower limit, it's 0 minus 0. So it's going to be 500 and, oh, no, it's going to be a little bit bigger than that. So those are your two values. So 3875, so 3,875 foot-pounds is going to be the total amount of work done lifting not only the weight, but the chain or the cable. And again, the cable's weight is changing throughout the act of winding up and getting that 40-pound object all the way up to the top of the building. All right, so stay tuned for the third video on physical applications, and so we'll be looking at, removing or draining water out of the top of a tank. So we'll see you next time.